All right. Okay, hello. Welcome to another class of CS867 QIC890. And this week we'll be talking about quantum walk algorithms. Okay, so to understand the quantum walks, it's best to start with classical random walks. And in this case, we mean random walks on a graph. So generally, in general setting, we're going to have a matrix that will specify. So the rows and columns of the matrix will be indexed by some set, say a set of vertices. So we have a set S here, which is the set of rows, and also the set of columns is also indexed by S. And the entries of the matrix over here, they basically they determine the probabilities of the transition, the probability of transitioning from one state to another. So for example, let's suppose that we just draw the following graph. And so we have 3 nodes here. So S will be size 3. And then we can have, if we're in one of these states, say this vertex over here, we can transition to either of the other 2, and their transition probabilities, like 0.3 and 0.7 over here. And similarly, now if we're in one of these other states, then we have probabilities of moving back to the other 2. And the probabilities coming out of each vertex sum to 1. So maybe something like this. Okay, so in this case, we're going to draw a matrix that basically specifies, we'll organize these numbers in a matrix. And here, so I guess the way I put it here, we had no self loops. You don't stay in the same spot there. So we have zeros on the diagonal. In general, you're allowed to have self loops. You have allowed to have self loops. So for example, here from transitioning to from this vertex to this one, we have a 0.7. So if we label this vertex 1, 2, 3, then we will put here, let's see, a 0.7 here and a 0.3 there. Okay. And then from vertex number 2, we will have probability 0.1 of moving to vertex number 1 and probability 0.9 of moving to vertex number 3. And finally, from vertex number 3, probabilities will be 0.4 and 0.6. Okay, so the way we have it here, we get a matrix where the rows of the matrix sum to 1. And they determine the transition probabilities. So the way this usually works is that we will basically apply this matrix to a vector that represents the state that we're currently at. So if we're currently at the first vertex, for example, then this will be the vector 0, 1, 0, 0. So here we'll write it as a row vector. So in general, so usually we apply matrices to column vectors by default. For some reason, when it comes to Markov chains, and sometimes people apply matrices to row vectors. Of course, there's not any difference. We could take the transpose of this matrix and just apply it to a column vector. So I'm not really sure, when the convention is that you apply it to a row vector and when it is that you apply it to a column vector. I usually like to apply matrices to row vectors, but of course, there's not much difference in this case. Okay, so here, if we apply this matrix, then the result will be a probability distribution. So we will have, we will have a vector in this case 0, 0.7, 0.3, which will tell us the probability distribution of where we are now. Okay, and we can apply this transformation again, or we can apply the matrix again, and we'll have an updated probability distribution. Okay, and so this matrix basically defines a random walk, and the state at each position, at each time point in the random walk will be a vector that has non-negative entries that sum to 1. Okay, and that determines the probability distribution over which state we're in, which vertex we're in. Okay, so in general, there's a theory of these Markov chains or random walks, and so I mean one basic property we want that we will kind of insist that our walks have was that they're connected. You can reach from any state to any other state. So for example, you don't have a situation like this where, for example, these two vertices reach each other and this one doesn't reach them. So although you could define such a walk, you know, we are not really going to care about it because it separates out into two walks that don't talk to each other. Okay, so we'll basically only be interested in these irreducible Markov chains or random walks that that don't have this property, that where every vertex can reach any other one with non-zero probability eventually. Okay, so that's one thing, and the other is sometimes, so often we're going to care about reversible walks where basically where this graph is going to be undirected. So going forward and going back has the same probability here if the graph is undirected. And in that case, the matrix will be symmetric. So the rows and columns will both sum to 1. So one of the main properties of a random walk is called the mixing time. And it turns out that every random walk has what's called a stationary distribution, so long as the random walk is irreducible. It has what's called a stationary distribution. This is a distribution, a vector, such that if you apply this matrix to it, you get the same vector back. Okay, so it's a distribution such that if we start from this distribution and take a random step according to the walk, the distribution, the new distribution over the vertices is exactly the same as the one we started with. Okay, and it's actually, in terms of linear algebra, this is just going to be an eigenvector whose eigenvalue is 1, because the matrix preserves the vector, right? So this means this is an eigenvector of eigenvalue 1. And moreover, we want it to have non-negative entries so that it's a probability distribution. Okay, so this is a non-negative vector that's an eigenvector with eigenvalue 1. And it will also turn out that every other eigenvalue of this matrix is at most 1. If the walk is something that's called aperiodic, then all the other eigenvalues will actually be strictly less than 1 in magnitude. Okay, so we're going to have okay, so the key concept here is, one is the stationary distribution. The stationary distribution being the unique vector that's non-negative and has eigenvalue 1 as unique. Every other vector has eigenvalue whose absolute value is at most 1. And so generally, for the types of walks we care about, for walks that are aperiodic and kind of nice, for example, the symmetric ones, we are going to have what's called an eigenvalue gap. We're going to have a spectral gap between the largest eigenvalue, which is 1, and the second largest eigenvalue. Okay, and so if we kind of order all the eigenvalues of these of this matrix, the largest will be 1, and it will correspond to the eigenvector, which is the stationary distribution, which is the special distribution that we will basically reach if we walk forever. So if we keep walking, we'll basically eventually converge to the stationary distribution, no matter what distribution we start with, assuming you know that the walk is irreducible and aperiodic and so on. And then we will have a second eigenvalue. The second eigenvalue will have, so it'll have some eigenvector that corresponds to it, but it will generally be strictly less than 1 for the walks we care about. And the difference between them, the 1 minus lambda, the difference between the largest and second largest eigenvalues of our random walk is called the spectral gap. And it basically determines how fast we're going to converge to the stationary distribution. The intuition is roughly that we have our true stationary distribution, which has this eigenvalue. And if we keep applying the matrix, then the component that corresponds to this kind of stays fixed. The component of the vector that kind of corresponds to the eigenvector of second largest eigenvalue will decrease as we apply the matrix, but it will decrease like something like lambda to the t if we apply it t times, right? So if we apply, I mean, if we kind of write out any vector x as a in the spectral in the spectral basis, basically the basis of eigenvectors for the matrix, assuming the matrix is orthogonally diagonalizable, then if we write x as kind of the sum of these eigenvalue times eigenvector, so like lambda 1 v1 plus lambda 2 v2, then these are coefficients, I guess. Maybe I should use a different variable for them. Okay, let's call it C1 v1 plus C2 v2. So if I apply the matrix to x, then what will happen is that each of these we can apply the matrix to each of these eigenvectors separately, and doing so will basically multiply each of them by the corresponding eigenvalue. And if we do this t times, then we're going to get something like this. And so what's going to happen is that the component that corresponds to the largest eigenvector will dominate when so the largest eigenvalue rather. So the component, the eigenvector of the largest eigenvalue will dominate as t goes to infinity, and the rest will sort of vanish in comparison. And the rate at which the rest vanish, so the amount of time before these basically become less than some constant, will so it will basically be this difference between the largest and second largest. So if the largest eigenvalue for us is 1, so the difference between the largest and second largest eigenvalue is an important quantity. It's sort of the t we need to pick before kind of everything else decreases to less than a constant. It's proportional to So that t is proportional to 1 over this difference, okay? Okay, so that's sort of the basics of random walks. And so we can imagine a situation where we have some graph. Okay, so let's say we have a graph that looks like this. Okay. We have a graph and we are starting in some vertex, or maybe in a distribution over these vertices. And then we walk some number of steps. And we are looking for a marked element. So maybe there's a circled element there. And so we want to kind of find it by walking along the graph. And so in general, like the way we're going to think about it, and this is sort of explained very nicely in the survey paper by Miklos Santha. So the way we're going to think about it is we're going to consider the cost of 3 operations. Okay, so one operation is called the setup cost, and this is going to be S for us, and that's going to be the cost of sampling a random vector from the stationary distribution. Then generally that will just be uniform. So this is just going to be the cost of picking a uniformly random vertex. Okay, so this is S. We will also have another cost called U. This is it's called the update cost. It's the cost of taking a step in the random walk. So stepping from one vertex to a neighbor at random. Okay, so this is the update cost U. The update cost might be much smaller than the setup cost. So it might be very expensive to pick uniformly random vertex in this graph for some reason, but walking to a neighbor might be much cheaper. And then finally, we're going to have a cost C for checking whether a vertex we're at is marked. Okay, so maybe that's expensive too, we don't know. So we'll try to write the bounds in terms of S, U, and C. And there's 2 more parameters that are important for us. One is the fraction of vertices that are marked. So this is epsilon. So here for us, it's, I guess, 1 over 6. That's the fraction that are marked. So note that while these capital letters are like bigger than 1, basically, epsilon is smaller than 1, and our complexity will depend on 1 over epsilon in general. And finally, we're going to have delta, the parameter delta, which is controls the mixing time. It's the spectral gap between the difference between 1 and the second largest eigenvalue of the random walk. Okay, so that depends on kind of the structure of the graph and what the weights are. And generally, we're often going to just use unweighted graphs, which basically means that a random walk is we walk to a uniformly chosen neighbor. So in that case, we can calculate the spectral gap delta of various graphs. And this will be less than 1. So again, our complexity will generally depend on 1 over delta, which is the mixing time. It's the amount of random steps we have to walk before we basically reach a uniformly random vertex. Okay, before no matter where we started with, if we walk 1 over delta steps, we've basically just reached a random vertex. Okay, so in terms of these parameters, we can describe the cost of a search algorithm which walks along the graph, and this is all still classical. So a kind of very simple algorithm says, all right, why don't we don't even try any walk? We will only directly try to search for a vertex. So we will pick a random vertex, and then we will check if it's marked. And if not, we will pick another random vertex and check if it's marked, and so on until we find the marked item, or until we give up. So the cost of this is, well, each time that we want to check random vertex, we need to pay S for generating a random vertex, plus we need to pay C for checking it. And the number of times we need to do this before we can find the marked item is that is 1 over epsilon. So our total cost is s plus c over epsilon, where again, epsilon is the fraction of marked items. So we are not going to generally write a dependence on the number of vertices. We will do all our dependencies in terms of kind of 1 over epsilon, where epsilon is the fraction of them that are marked. Okay. So that's just a kind of very stupid algorithm that doesn't really do anything. Doesn't work at all. So this is not even a random walk, right? This is just some algorithm that we can describe in terms of these 5 parameters. But then we can do a random walk, which might be cheaper depending on the value of these parameters. And the random walk will work like this. So first we will start with the uniform distribution that we pay the setup cost. So we pay the setup cost, and then what we do is we will take random steps. So it costs u per step, and we will take 1 over delta of them. So we will pay u over delta in order to get to another random vertex. Okay, and we pay u over delta to get to another random vertex, and then we check that vertex, and then we see if we find the marked item. And if not, we just repeat this procedure without the setup cost. So the initial setup cost is sort of, just a cost of finding the first vertex to begin with, just finding any vertex to begin with. Then the cost of kind of re-randomizing is going to be u over delta to get to another random vertex, basically. And then we check it, and then that's checking 1 vertex. So we divide all of that by epsilon, because we need to check 1 over epsilon different vertices before finding the marked item. So we can do everything in kind of this cost, the s plus u over delta plus c over epsilon. And so, if the setup is expensive, if it's pretty expensive to find a vertex from scratch somehow, but easy to walk, then we can have some savings here, especially if this update cost is particularly cheap. So okay, that feels like kind of a weird thing to happen, but it will happen more in the quantum setting, generally, but it can happen classically too, with that sort of constructing even a single vertex at the beginning is expensive, but moving to a neighbor is cheaper because you only have to modify the description of the vertex slightly. So you're coming up with the description of 1 vertex is very complicated, but modifying that description so that it describes a neighbor is very cheap. So that can happen. So this algorithm can be a useful algorithm for finding a marked item as well. Okay, and of course if checking is very simple, is very easy, then we could just do something like this, set up, and then so first we set up, and then each time we do an update, a small step. We don't even get to a uniformly random vertex yet, but we get to some vertex. We can check if checking is for free. And then we can just make sure to do this enough times to guarantee that we find the marked vertex, and that would mean that we have to do it 1 over delta times 1 over epsilon times. So we can get an algorithm with a complexity like this. This looks strictly worse than this. Okay, so in general, this algorithm is not any improvement over this one, but that's basically because we're assuming that we have to pay 1 over epsilon times 1 over delta in the worst case. And sometimes there's a clever analysis that tells you that, okay, even though if you only take a single step away from the vertex you just checked, you take 1 step away, that doesn't get you to a uniformly random vertex. Still, your chances of already finding the marked vertex is not as is not 0. It's not as bad as you know, as if you keep checking the same vertex again and again. It's not that bad. So so if you have a better way to analyze what happens in this walk, then you can improve this denominator to something better. And so this kind of algorithm might be an improvement if you somehow can improve the analysis. Okay, but we don't have a black box bound that's better in terms of just epsilon and delta in the general case. All right, so that's classical walks. And now for quantum walks, so I think the easiest way to talk about quantum walks is to just, you know, describe it in terms of exactly the same parameters. So for quantum walks, we're again going to have some graph, and we're going to again have some marked vertex. And so, you know, again, okay, so let's draw this again. And okay, we have a marked vertex. And so, okay, of course, we're going to do everything in superposition now. I don't want to get into the details of exactly how the quantum walks work. And there's the survey by Miklos Santha goes through it, I think, in a nice amount of detail, and kind of tries to give some intuition for how it works. The more important thing I want to emphasize is the dependence on the parameters that you can just get via these quantum walks algorithms that have been described. So first of all, we need to talk about the parameters again. So we're going to have the setup cost of getting into some kind of getting some kind of quantum register that stores a vertex, or hopefully a superposition of the vertices, depending on what's required. And then we're going to have an update cost for basically applying a unitary that sort of performs the steps of the quantum walk, and we'll have a check cost, right? And all those need to be implementable kind of in coherent superposition. So again, we won't really go into the detail of what these means, especially how to do an update. I mean, what that means in the quantum setting. Okay, epsilon is still exactly the same as before, as a fraction of marked vertices, and delta is the same spectral gap so exactly the same classical matrix that we had. We're not really even changing that. Okay, so just for that same classical matrix, we have the same delta. Okay, but we're going to walk differently. We're going to do a quantum walk instead of a classical walk. Okay, so we didn't really change any of these. Well, we didn't change epsilon and delta, and these costs SU and C are directly analogous to their classical versions. Okay, and so I guess the main kind of, well, the main quantum walk result that at least so far as described in the survey, and so far as we'll go over for now, says that with a quantum walk algorithm, you can find a marked vertex with cost, which is a setup cost plus 1 over root epsilon times 1 over root delta u plus c. Okay, so this is going to be the cost. And remember that to compare, the classical walk had cost. That's s plus 1 over epsilon 1 over delta u plus c. Okay, so we bought a square root in delta and a square root in epsilon. Okay, so we gained this by doing things quantumly instead of classically. And so, you know, this square root of epsilon feels like Grover search. Well, maybe they both do. You know, if we have n, if we have n elements and one is marked, then epsilon is 1 over n, and we can sort of find it in proportion to 1 over root n. quantumly. Okay, and this governs the mixing time. This governs kind of how many updates we need to make before a vertex we're picking looks uniform again. And that we can get a quadratic saving in as well. And so, so this is kind of a very convenient framework to describe algorithms. Okay, so once we know about this framework, we can just directly define graphs and immediately kind of, well, we need to calculate spectral graphs, fine. But then we can immediately kind of get quantum algorithms as soon as we calculate these 5 values. Okay, then we can get a quantum walk algorithm just by doing this calculation. So let's do an example of this. So I guess the main example, and sort of the first example, which was essentially the first time that quantum walks were described, or at least quantum walks of this form were described. This was due to unbiased, and it's for a problem called element distinctness. So this is a query problem. We have it's a Boolean function. So here we have that f of x equals 1 if xi equals xj for some I and j, and then 0 otherwise. So here the input string has alphabet size n here, and we basically care whether there's 2 cells that have the same element, or if the elements are all distinct. Okay, so this is called element distinctness. Okay, so this is the function f, and we're interested in the quantum query complexity of it. And so you might imagine, okay, so we're searching for something, right? We're searching for a pair of cells that have the same content, that have the same item in them. So why not do Grover search, right? But the issue is that if there's n bits here, or n alphabet symbols in the string, then there's going to be n choose 2 pairs to check, right? Which is roughly n squared. So a Grover speedup on searching all n squared of them will give you cost n. So Grover search here is going to run in O(n), basically. Instead of just searching n squared pairs, you can do it in n time. Fine, but there's the string is only of length n. The string is only of length n, so just reading the whole string only costs n. Okay, so Grover search didn't give us any speed up over the classical algorithm that reads all the bits of the string and checks if any 2 are equal. Okay, so we're going to improve on this trivial algorithm by using a quantum walk. And the quantum walk is going to be not over this string actually, but over a graph that we have to describe, that we construct. And it's going to be the Johnson graph. Let's talk briefly about the Johnson graph. Okay, what is the Johnson graph? The Johnson graph, it has kind of two parameters, n and r. Actually, I don't know which letter to give it, but okay. So the vertex set is the set of all r element subsets of an n element set. Okay, so it's This is the set of all, subsets of an n-element set such that the size of the subset is equal to R. Okay, so we have, imagine n elements of a domain, for example, n bits of the string. So our vertex set in the graph is going to be all choices of R elements out of those. Okay, so the size of this vertex set is exactly n choose R. Okay, and here n and R parameters for the Johnson graph. And then we say that two vertices are adjacent in the Johnson graph if they differ, if basically they differ in only one element. Basically, if the symmetric difference is 2, is size 2. So that means, like, basically you can get from one set to the other by deleting an element and adding a different one. Okay, if you can get from let's say set S to set T by deleting one element and adding another element, then S and T are adjacent in the Johnson graph. Okay, and that's an if and only if. So that defines a graph. Okay, so in particular, let's see. So the degree of each vertex. What is the degree of the vertex S? Well, we have R choices of what to delete, and then we have n minus R choices of what to add back in. So each vertex has degree R times n minus R. Okay. So this is the Johnson graph, and okay, so well, we're gonna do a quantum walk on it, and so the way this is going to work is that the graph is going to be R sets of size R of alphabet symbols from our input. So we have X is some n-bit string of input, and we're going to pick a set of size R, and such a set is going to be marked if it contains two different indices, basically, where xi equals xj. Okay, so we say S is marked if there exists ij in S such that xi equals xj. Okay, so the graph itself doesn't depend on the input, but which elements are marked depends on the input. Okay, so we're going to calculate the setup costs and update costs and so on. So okay, so to consider the setup cost, well, to set up we have to pick a set of R elements, and we're actually going to want to read all of them in order to kind of check that there aren't any duplicates within that set, that we're not starting at a marked vertex. So we're going to read the set of R bits, and we're going to do it in uniform superposition over all such sets of R elements. Okay, so the cost of doing this, well, reading R bits costs R. Okay, so it costs us R queries to kind of do a uniform superposition over sets of size R. So over R vertices for the Johnson graph. So that's the setup cost. Then the update cost. Well, to do an update, we want to move from one vertex to an adjacent one, which means we want to move from one set of R elements to another, to an adjacent set, which means delete a vertex and add a different one. So to add a different one, all we need to do is query the new position in X. Okay, so we can perform an update. So we have setup is equal to R update. We can perform an update in O1 queries. Okay, and then finally checking. We can perform a check by so I guess in the way we set it up here, we've sort of already read the elements that that are in the vertex. So to perform a check, we're actually going to call it the cost of 0. Okay. Okay, so now how many elements are marked? Well, the sets that are marked are those that contain 2 elements that are identical. Okay, so in the worst case, so let's assume that there is a marked vertex. So in the worst case, there's only 2 positions that are identical. And so if we pick a set of size R at random, the chance that it contains both is, well, the chance that it contains the first one is R over n, and the chance that it contains the second one is roughly R over n as well. So it's roughly R squared over n squared chance that it contains both. So the proportion of marked elements is roughly R squared over n squared. So this is epsilon. Okay, and finally delta. Delta depends only on the Johnson graph, so we can basically just look up the eigenvalue gap, the spectral gap for the Johnson graph, which turns out to be 1 over R. Okay. So this means that our final cost for the quantum algorithm, where we do a setup of cost R plus, we pay 1 over epsilon, 1 over root epsilon, update sequences of updates and checks, and the sequence of update 6 cost us 1 over root delta U, and then a check cost C. So this is the setup cost here. So we have R plus n over R times root R times 1 plus 0. Okay, so we get R plus n over root R as the final cost. And this is minimized when R is equal to n to the 2/3, in which case the final cost is n to the 2/3. Okay, so using this quantum walk, without even really going to the detail of how it works, but just kind of doing a black box check of all the parameters and plugging it into this formula, we get a quantum walk algorithm for element distinctness, which uses n to the 2/3 quantum queries instead of the trivial n. And this turns out to be tight. So there's an omega n to the 2/3 lower band. Okay, so we actually get a tight algorithm for element distinctness in this way. So let's do another example. Okay, so another simple example is a problem called matrix product verification. And here the setting is that we're given query access to 3 matrices. So let's just try it like this. Okay, and let's just suppose they're square matrices. And the question is this true? So, we can query the entries here. So we have, I guess, 3n squared bits that we can query, right? We can query in any of the matrices, and we just want to know whether this is true. Okay. So we're basically searching for an entry here, which is not equal to the corresponding, row here times column here, right? So if this is kind of I and j, then we want to look at the row I here and the column j there and see if the inner product of them is equal to this entry or not. So our search problem is basically searching for such a position where they're not equal. Okay. And so what we'll do is we'll basically, have, well, as usual, we're going to have a quantum walk over the Johnson graph. It kind of, so strangely, even though quantum walks are kind of defined in this general setting, in practice, when we apply it to such, query problems that don't look like graphs we want to walk on, where we construct the graph we want to walk on, then generally the graph we pick that we want to walk over is going to be the Johnson graph. So effectively, quantum walks, much of the field of quantum walks is really quantum walks over the Johnson graph. Okay, fine. So what is the Johnson graph here? How should we define it? What should be the domain of it? So the domain of the Johnson graph is going to be the set of all row indices or column indices. We'll assume the matrices are square. So we're going to have each vertex of the Johnson graph be a set of size r of row indices or of indices for this n by n matrix. And we're going to say that such a set is marked if basically within the rectangle defined by the set within C. So like if we're defining some kind of rectangle here where we're looking at these rows and columns, which corresponds to kind of blocks like this over here. If that contains an error, if that contains a position which is not equal to the inner product of the corresponding row in A and column in B. Okay, then in that case, then the set of indices is marked. Okay, so so the setup cost here is going to be, let's see, the setup cost for us is going to be just r times n, right? Because basically reading this section is going to cost us r squared, right? Reading this section is going to cost, this section is r by n, and this is also r by n over here. So it's going to be order r by n to set up, to read all the corresponding bits. And we are, again, going to do this in superposition over all choices of sets, so that we start with a uniform superposition over the vertices of the Johnson graph. But now to walk, then we just remove, well, we remove an index from our set and add another one. So that means we remove a column here and query a new column, query a new row over here, and we query a new row and column over here. So this costs us n plus 2r, I guess, to query all these new, that's r. So that's order n to update. Okay, so the setup was order rn. The update is order n. Okay, and again, the check for us is going to be check for us is going to be cost 0 because we assume we already read everything when we go to a vertex of the Johnson graph. So that doesn't have to be true. In general, we can do a walk over the Johnson graph where each time we do an update, we don't read everything. We, maybe only partially read. So that it's also possible to set up quantum walks that way, and then kind of define the check separately. But for now, we're just going to define the check to be 0 and the update to contain kind of all the work of reading everything. And then, okay, so what is the proportion of marked elements? Well, if there's going to be at least one contradiction in, well, suppose in the worst case there's one contradiction in the target matrix C, in the kind of answer matrix C, then if it's position I, j, then we need both I and j to be in our set. So the chance that I is in our set is R over n, and the chance of j is in our set is roughly R over n as well. So we can do R squared over n squared. We can set that as epsilon. And finally, delta for the Johnson graph is always 1 over R. So the final cost is S plus 1 over root epsilon 1 over root delta u plus c, which is Rn plus n over R root R n plus 0. And we get here Rn plus n squared over root R. So optimizing over R, then we again pick R equals n to the 2/3. Okay, in which case we get here the final cost is n to the 5/3, which is a little less than n squared. N squared is a trivial algorithm, so we can improve over the trivial algorithm by doing this this walk. And so the Miklos points out that the best known lower bound is actually n to the 3/2. I'm not 100% sure whether there's been work on this since to try to improve this lower bound or the upper bound, but it's interesting that if for such a simple problem there seems to be a gap. I guess to be 100% sure there's still a gap, I would have to look this up. But I haven't really seen any recent papers on this problem. I suspect that nobody's really worked on this, so that we still have this interesting gap between the lower bound, the known lower bound and upper bound. Okay, but I should probably check that. Okay, so Miklos has a few other examples. So I encourage you to go through that. So I think we will stop here for now. Some examples have the checking not being cost 0. So that's, of course, good to see as well. There is an example that even does not walk over the Johnson graph. Okay, but really most times you do a quantum walk, you do want to walk over the Johnson graph. So the trick will be actually to pick where is the Johnson graph, right? What sets, what is the domain and what sets are you kind of searching over that you want to pick? And that's kind of because the Johnson graph is it's a natural graph for where the update is cheaper than the initial construction of a vertex, right? So picking one vertex in the Johnson graph costs you R basically to read R things usually, or it consists of R things, but to update it, you only delete one and add a different one. So updating is generally much cheaper than finding a vertex from scratch. And so the Johnson graph is a natural graph to try to get these quantum walk algorithms to give you speedups. Okay, and finally, there has been kind of more work on different generalizations of quantum walks. So this bound here, S times 1/√epsilon plus 1/delta U plus C, it's not kind of the final end of all quantum walks or anything. So this is only this one commonly used type of quantum walk. This is not the only thing quantum walks can do. And in fact, of course, we didn't even go through the details of how this quantum walk works. But you can change those details as well and have different analyses and different quantum walks. And so the readings, so Miklos doesn't really go into such generalizations, but in part because he published his survey a long time ago. But the three readings that I've assigned all include kind of more interesting things you can do with variants of quantum walks. So you should check those out as well. So well, you can't always assume that quantum walk always means just exactly this, especially over the Johnson graph. On the other hand, if you ever find yourself wanting to construct a quantum query algorithm and you think, oh, why not try quantum walks? The first thing to try is kind of this thing over the Johnson graph, and not anything more complicated. And this way, you kind of have a black box way to construct a quantum algorithm without needing to get into the details of superposition and so on, but instead only kind of check setup and update costs and so on, kind of basic combinatorial things like that. Okay, so we'll stop here, and on Monday we will take up 3 presentations for the assigned readings, which you can find on Pieta. All right.